Hello. Good afternoon, good evening, everyone. A warm welcome to all of you present over here. I am Nidhi Verma, research scholar at IIT Bombay, and today I am the coordinator of the session here in South 2. I welcome you all for the session. I am delighted to welcome our esteemed chair, Professor Raghuram Amajwala, and our co-chair, Professor Vipin Kumar Gupta, to this session. It is also my pleasure to welcome Professor Men Xia Wang, who will be delivering the thematic lecture in this session. Along with him, I welcome all the presenters and participants to this session. Now, I would like to give a short introduction for our chair. Dr. Raghuram Amajwala is an assistant professor in the Department of Civil Engineering at BITS Pilani, Hyderabad campus. He holds a PhD from IIT Hyderabad and has completed his postdoctoral research at IIT Bombay and Aalto University, Finland. His research focuses on unsaturated soil mechanics, rainfall-induced slope failures, municipal solid waste stability, and sustainable ground improvement. Dr. Raghuram's work integrates geotechnical engineering with sustainability, addressing emerging challenges in soil and slope behavior under changing environmental conditions. Our co-chair for today, Dr. Bipin Gupta, is an assistant professor in the Department of Civil Engineering at IIT Kanpur, who holds a PhD in geotechnical engineering from the University of Waterloo, Canada. And his research focuses on foundation engineering, soil structure interaction, computational geomechanics, soil dynamics, and offshore geotechniques. Dr. Gupta actively contributes to advancing geotechnical research and education through his work on dynamic and computational modeling of the soil foundation systems. Now, I would request Professor Raghuram to preside over the session and introduce our thematic speaker for the day.
Thanks, Nidhi, for the introduction. Warm welcome to all of you. I'm Raghuram. I would like to introduce our thematic speaker, Professor Mang Wiang Weng. Dr. Weng is a distinguished professor in the Department of Civil Engineering, Civil and Environmental Engineering in National Yang Ming Chiang Tung University, Taiwan. He holds a PhD in Civil Engineering from National Taiwan University, and he is a registered professional civil geotechnical and structural engineer in Taiwan. His research experience spans rock mechanics, geomaterial constitutive modeling, landslides, and disaster prevention technology, and numerical analysis using DEM and FEM methods. With extensive academic and professional experience, including his tenure as a professor at National University of Kaohsiung 2013-17, Dr. Weng has made significant contributions to advancing geotechnical and rock engineering practices in both academic and applied context. Now I would like to request him to deliver a thematic lecture on hydromechanical coupling analysis of carbon dioxide migration in saline aquifers. The floor is yours. You have 15 minutes to present it.
Okay, thank you for your introduction, Chairman. So let me open the file on the laptop. That's that. So do I have a pointer? No? Okay, it's okay. So good afternoon, everyone. It's my pleasure to share my research. So I'm Meng Xia Wang from Taiwan. Okay. So okay, it's okay. Okay. So today it's my pleasure to share my research. My research is focusing on the carbon dioxide storage. So at the beginning, this is my introduction. In Taiwan, the major sources of carbon dioxide emissions are concentrated along the western coastal area, in this area. So at the meantime, the foothills and the plains of western Taiwan provide the most suitable geological formation for the CO2 storage. So these emission sources overlap with the potential storage sites. So it highlights the region's importance for CO2.
Okay. Thank you.
For CO2 mitigation. But in this study, we focus on a practical problem. We want to clarify how CO2 injection affects the capillary stability during the injection. So here are the objectives of this research. At first, we try to develop a hydromechanical coupling model to simulate the CO2 migration and the corresponding stress response of the cap rock during the injection process. And then we validated this coupled model through a benchmark problem to ensure its reliability and accuracy. Then based on this model, we apply it to a field scale case in central Taiwan to evaluate the cap rock integrity and identify the self-injection condition for CO2 storage. So here is our methodology. At first, we adopted the software COMSOL Multiphysics to model the compressed hydromechanical coupling. But here we do two kinds of analysis. At first, we have to consider the two-phase flow analysis. So we use the Van Jacobson model to characterize the relationship between the CO2 and the water. And we have to consider the relative permeability. So here are the equation for the saturation considering the CO2 and the water. And then we also consider the capillary pressure and the relative permeability. And after we perform the two-phase flow analysis, then we have to consider the hydromechanical coupling interaction. So here we adopted a very common failure criterion. In rock mechanics, we use the Drucker-Parker to evaluate the failure of the rock. And then we define a factor, we call it a damage factor, to assess the degree of potential failure in the rock. And then we also evaluate the deformation of the cap rock. So we adopted the Devtoric strain to evaluate the deformation. So but after we have this established this theory, so now we use this model to analyze the benchmark problem. So this is a very simple benchmark problem. So here we have two aquifers, and in this area we have a impermeable rock, impermeable layer. So we inject the CO2 into this reservoir. Then here is another observation well, so we can monitor the leakage of the CO2 through this well. And then this is the model for the COMSOL Multiphysics. And here are the parameters for the benchmark. So this is our simulation results. We can compare with the literature. So in the left-hand figure, you can see this is the results from the literature, and this is from our simulation. Our simulation agree well with the literature. And in this simulation, we consider the CO2 saturation. Then we also consider the pressure distribution. So for the pressure distribution, this figure shows the result in the literature, and here is our simulation result, and our result is consistent with the result in the literature. So we also consider the leakage ratio in our analysis, so we can compare the results in the previous studies. So in this figure, you can see the blue line shows our result. It agree well with the previous result. So based on this simulation, we can confirm our simulation are consistent with the previous study, and this study based on the two-phase flow analysis. So after we verify our two-phase flow analysis, we have to consider the hydromechanical coupling analysis. So in the original numerical benchmark problem, it assumed a completely impermeable layer to simplify the Cape rock properties. But it is uncommon in real world. So we have to consider the properties of the Cape rock. So in this model, we consider the properties in our model. And the properties of the rock are obtained from the shear in Taiwan. And we also set up 3 monitoring points in our model to capture the temporal evolution of the mechanical response. Okay, so after we consider the Cape rock, you can see the overall trends are very similar with the previous result, but here we can see some CO2 penetrate in the Cape rock. And this is the CO2 saturation, and this is the result of pore pressure. And we also can see calculate the damage factor. So based on our calculation, we find that the damage factor was about 0.54. It is not very high. So it indicates that the formation remained stable without failure. So next, we consider the distribution of Davidovic strain, and we can see most Davidovic strain was developed around the injection well. When we increase the injection rate, then we will find the higher Davidovic strain. So after we got the results of the benchmark analysis, then we consider a field scale simulation. So we adopt the Taichung power plant. Taichung means central Taiwan. So this site is located in central Taiwan. And in this area, we have 2 typical geological formations. One is the shear, Jinshui shear, and the other one is Guizhulin sandstone. So these 2 rock layers are very suitable for CO2 storage because they have sufficient thickness and favorable permeability, and the relatively less affected by the tectonic deformation. So here are some results. In our simulation, we consider 5 different injection rates, and the total injection volume is not high, just 2,000 tons, because this is a pilot test. And then we check the bottom bore pressure, and we find after the injection, the pressure at the bottom hole increase, but then it stabilized around about 25.5 megapascal. And we also check the shear stress, and you can see the shear stress varies a little. So just 0.7 megapascal, it did not affect the stability of the Cape rock. So here you can see the damage factor. The damage factor increased in the initial stage, but it stabilized in the following injection, and we think it does not affect the stability of the rock. So finally, it's my conclusion. In our study, a coupled hydromechanical model was implemented in COMSOL multiphysics to simulate the CO2 migration and the leakage during the geological storage. And our analysis showed good agreement with published data, and we confirm its reliability. And based on this analysis, the maximum damage factor indicates no failure. And during the field scale injection, the caprock increased slightly. So it suggests that CO2 injection did not compromise the caprock integrity. So thank you.
Thank you, Professor Wang, for such a great presentation. Now the floor is open for discussion. Do you have any questions?
No? Okay. Thank you very much. Okay.
So I have two questions.
Okay, please.
So while injecting the carbon dioxide, so are you collecting the carbon dioxide from somewhere, or are you capturing from the atmosphere?
Okay. The CO2 source are from the power plant, because the site is very near the power plant. This is a very large power plant, so the CO2 emission is very high. So we can collect CO2 at this site and to inject in the storage site.
Okay.
Yes. Mm-hmm.
And in one of the slides, you were mentioning about the higher the pressure, lower the migration rate. So what is?
Okay.
Are you talking about the pressure or the quantity? Higher injection rate.
Okay,
Yes.
you mean this one? Okay, because the total volume is about 2,000 tons.
Okay.
So if we increase the injection rate, the duration will be shorter. So we will find that the higher injection rate leads to a small migration rate, because the total injection volume is fixed.
Okay.
Okay.
Thank you. Thank you.
Thank you. Okay. Thank you.
Thank you very much. Now I would like to request our chair and co-chair to present a small token of appreciation to the speaker.
Now I request Professor Bipin to start the session.
So, having completed this thematic lecture, let's begin with our contributory presentation. So the first presentation is titled An Innovative IoT-Based Alert and Monitoring System for Rockfall and Debris Flow Mitigation Systems, Geostability Monitoring and Events, Case History. The authors are Rudra, Ratnakar and Domenico, and the presenter is Mr. Fabian Gazzardo. So please, Mr. Fabian, go ahead and present. You have 9 minutes.
Ooh, challenging. Can you hear me? Okay. So after the accent from Taiwan, you have the French accent. So I hope that you will be able to understand my accent. So yeah, good evening, good afternoon. So my name is Fabien Gazzardo. I am the responsible of the mitigation protection system at Macaferri. So I'm based in Italy. And today presentation, I will briefly walk you through our main features of early warning system called ELOMAC, and I will present to you 2 case studies. So before diving into the technical aspects, I would like to start with a few quotes. So here is the first quote from the World Bank. Okay, disasters caused by natural hazards are increasingly threatening lives and livelihoods. Climate change is further exacerbating the negative impact of disasters caused by natural hazards, and twice as many climate-related disasters have occurred in the last 20 years compared to the previous 20-year period. And the second quote is this one: is all people on Earth must be protected by early warning system within 5 years. Okay, and this quote is from Antonio Guterres, the former UN Secretary. So McAfee has developed a system, early warning system called ELOMAC. Here you can see this system. So ELOMAC is a disc-shaped device, okay, with a diameter of 30 centimeters, which is designed to be very light and easy to handle. From its body extend 8 tie ropes, each one connected to a different sensor, and this allows you to monitor up to 8 different points with a single device. Thanks to its low weight, it can easily be transported to hard-to-reach job sites, conditions that are common in many locations, ensuring reliable performance in every situation. Okay? As I mentioned, most rockfall protection systems are installed in remote areas without any power supply. So this is not a problem for ELOMAC. It is self-powered with long-lasting batteries. Maintenance is practically zero. And once installed on the protection system, it only alerts you in case of impact. So in terms of communication, ELOMAC uses a state-of-the-art transmission system based on IoT technology. So each ELOMAC device sends its signal with a LoRa protocol on a dedicated frequency to a central gateway, which is act as a receiver and a repeater. And from there, the alarm can be transmitted through satellite, GSM, or LTE, ensuring that the information is delivered in any situation. So with this technology, in the event of an impact on a rockfall protection system, the alert is received by the responsible person in less than 1 minute. And this is the maximum timing. Usually it's less than 1. So how the alert is received by the person? So in any way the person can decide, from SMS, email, WhatsApp, or app notification. So there is a dedicated app that has been developed by our company, and it's available on iOS and Android, and it allows you to monitor the system status in the most effective way. So the ability to check the daily status of every sensor on the app, geolocated map with colored dots showing each sensor and the status of each sensor. Additional information also available on the app, like the GPS coordinates and the battery level of the ELOMAC. So this is a general view, let's say, of the application of the ELOMAC, where it can be used, bringing a significant benefit to the efficiency of the solution and to the community they protect. So we can see on the first application is on barriers. So it can transform your barriers on smart barriers. So rockfall and debris flow barriers equipped with ELOMAC are always under control. So here you can see that the ELOMAC is installed on a post of the barrier, and you have the tied rods which are installed on the screen of the barrier. So it's very important to know when the barrier is impacted by a rockfall like this. You can ensure the correct maintenance of the system after an impact. Here, after we are going to see the second case of installation of ELOMAC. It's on a drapery system. So these pictures here illustrate how demanding this application can be for the installer. So in such cases, you see the LOMAC is installed on the slope, and the tie ropes are installed along the mesh. And when there is a specific movement of the mesh, there is an alert which is sent to the users. Other type of installation on the left can be retrofitting. So any old protection system can be equipped with a LOMAC. And another one we call geostability monitoring, and this will be the case study number 1. Okay, so here we are in the Italian Alps, in a location called Sonico. It's a very nice and beauty area, but two main geological elements define the risk profile of this region. First, there is the presence of an ancient paleo landslide along the Gallinina Valley. So it's a deep mass movement that is currently dormant, but which could be reactivated under certain conditions. And the second one is the side valley of Vararabia. Rabbia in Italian means anger, which generates very high energy debris flow. So mixture of water, mud, and large boulders. And these events are typically triggered by the combination of heavy rainfall and degradation of permafrost at high altitudes. So these are the risks I talk about. So in 2012, a big storm cell released exceptional level of rain of 180 millimeters in less than 20 minutes. And this, the soil was already very saturated with water, and about 300,000 cubic meters of debris were mobilized and rushing down the valley at a speed of 10 meters per second. So it was a very destructive force, okay, that destroyed the main road and the bridges. And this disaster was a marked turning point, okay, for the authorities that decided to install an alert warning system. So the solution was based on a two-level approach, okay. The first level was a weather station to monitor the rainfall, intensity, and temperature, okay. And the second level of the system was a LOMAC, which was physically connected to large boulders along the flow path, okay. So if a boulder moves, the sensor is triggered, and this provides immediate binary confirmation that a dangerous event is in progress. So the goal is clear, is to combine predictive alerts with physical confirmation, enabling authorities to act decisively and without delay. So here you can see the architecture of the system. So the system was covering an area about 14 square kilometers. So it includes the two weather stations that are the red dots, okay. 6 LOMAC Geo installed in green, which were installed along the flow path, 2 radio concentrators, 2 sirens, and 2 remote cameras. And the entire system operates on a private IoT system. So the logic of the system is based on the two-stage activation model, so pre-alert and confirmation. So the pre-alert is triggered by the weather station monitor rainfall in real time, okay? So there are some predefined threshold that if exceed the level of rain, send a notification to the firefighters, okay? And then there is a confirmation, as I was mentioning, if there is a movement of a boulder into the flow path, there is an alarm system to the population with the activation of the sirens and also some lights on the road that close the access to some bridges. Okay. So since its installation in 2012, the system has been successfully activated on several occasions, most recently in 2020 and in 2023, when about 250,000 cubic meters broke off from the valley and rushed into the valley, okay, carrying boulders as big as cars, okay. So in every case, the population of the two villages were efficient, and the population was evacuated on times. I go fast because I think I'm late. The case study number 2 is still in the Alps. So now we are not more anymore in Italy, but in France. Okay, so we are in an area which is at the border between France and Italy, and you can see here also the localization of steep rocky slopes, which is also an alternation between corridors and steep rocks. Okay, and here at the bottom there is the road here, going here from France to Italy. So, it's an important road for economic, for tourism, for ski tourism. Okay, so let's go fast. Okay, this is the one. Okay, so thanks to our expertise in geotechnical solution, McAfee was selected as a key partner to install some rockfall protection barriers from an energy from 750 kilojoule to 500 kilojoule. Okay, and Elomac was part of the solution. So at the core of the solution there was Elomac that was installed on the barriers. Here you can see the Elomac device. Okay. And let's say that the configuration was quite similar to the previous case study. So there was a light installed on the road. If there is an impact on the barriers, there is activation of the signal on the road, and the circulation is stopped. Okay. Here in the slide you can see the configuration. So at the bottom you have the road. Each green dot are Elomac. So you have several lines of rockfall barriers. And when there is an impact on one line, there is the activation of the system. And this is the end of my presentation.
So any questions from the audience?
It was super clear. Thank you.
Thank you. Thank you, Mr. Fabian Gazzardo. Yeah. So we'll go to the next presenter or the next presentation. The next presentation is on thermal, physical and mechanical properties of rock subjected to thermal shock by water treatment.
Warm welcome to one and all. My name is Kalanji Rugesh. I am from IIT Palakkad. My paper title is Thermal, Physical and Mechanical Properties of the Granite Subjected to Thermal Shocks by Water Treatment. And here nowadays the quest for sustainable energy has been increased interest in deep geothermal energy. Okay. Here I am showing one EGS model. Here we circulate cold liquid and get out it from hot fluids. Okay. Here at ground surface, at underground surface areas, there are networking of the fractures. Okay. Once we circulate that cold water enter into the reservoir, there due to temperature changes, there the cold water hits that hotter region. There we create that thermal shock. Okay. This is the to simulate those field into the laboratory purpose. I took one granite sample and that should be heated into the high temperature furnace. Then took those samples and into the take out the samples and dip into the water That's why they created the thermal shock on the samples. These are my objectives. First objective is I am investigating how the thermal shocks is created into the sample. Next, evaluate the thermal, mechanical and physical property changes, and conduct test under confining pressure of 5 MPa, 10 MPa, 15 MPa. Compare UCS and triaxial compression test. And this is a brief objective. Initially, we exposure to heat exposure to the sample and quenching. Later, due to that, thermal shock is created. Due to that thermal shock, microcracks are formed. After that, due to that microcracks, property loss might happen. Okay, overall, for these effects, reservoir is impacted. This is my experimental methodology. Initially, we mine granite blocks from near Bangalore area, and we core the samples in our college by using the core cutting machine and grinding machine. And after that, we put those samples into the oven for dry processing. After dry processing, we measure the physical properties, that is density and PV velocity. Later, we go for the heat treatment. Samples are put in the high temperature furnace up to 200 to 800 degrees centigrade is the target temperature with any heating rate of 5 degrees centigrade per minute. And that is held for a constant for 2 hours due to uniform heating within the sample. Next, quenching process. After that heat treatment, we take out the sample and suddenly dip it into the water to form the thermal shocks. And again, we measure the physical properties after the thermal shocks. And finally, we tested the thermal properties, that is thermal conductivity, specific heat, and thermal diffusivity. And mechanical tests are UCS test and triaxial test under the varying confinements. This is controlled heating and quenching cycles at multiple target temperatures. Yeah. This is physical properties of my results. Here, from density at 800 degrees centigrade, the density reduces by approximately 4%. Here, PV velocity reduced by 78%, because of the microcrack developed inside the samples. These are the thermal properties of Bangalore granite rock. Here also, due to microcracks only, the thermal conductivity is reduced with respect to the temperature, and specific heat is increased with respect to the temperature. Why the thermal conductivity is reduced means due to the thermal shock, there microcracks are formed, means voids are happen. Due to that, the contact between the solid particles are decreased. That's why the thermal conductivity value is reduced. Then these are the mechanical properties of Bangalore granite rock. Here there are 4 stages are there. One is compaction and elastic and yield and failure. In compaction stage, the curve should be in concave part. Under the confinement, the compaction stage, here we can see that is reduced due to that confinement, closure of the microcracks. And these are the conclusions. Density is reduced to 4% at 800 degrees centigrade, and PV velocity is reduced to 78% at 800 degrees centigrade. And thermal properties are that thermal conductivity and thermal diffusivity is reduced, and specific heat is increased, and mechanical behavior or stress strain curve become highly nonlinear at 800 degrees centigrade. And due to confining pressure, mitigates the temperature-induced microcracks. These implications are majorly in these results are critically useful for deep high temperature reservoirs, that is enhanced geothermal stresses systems and deep nuclear waste disposal facilities and deep mining and coal gasification projects. These are my references. Thank you.
Thank you for the nice presentation. So any questions from the audience?
Yeah.
Geothermal gradient of your study site, and what is the highest temperature in the site?
Actually, this is not taken from site. We taken from quarry some specimens. For that only we tested different temperature at different temperatures we created. Means 200, 400, 600, 800 like that.
Okay, I see. Okay.
Yeah.
Any more questions? Any more questions from the audience? No? So thank you. Thank you. Okay. So we'll go to the next presenter or the next presentation, which is on a generalized 3D implicit constitutive model for predicting uniaxial stress strain response of granite rocks.
Today I am here to present. Today I am here to give a presentation on the topic titled "A Generalized 3D Implicit Constitutive Model for Predicting Uniaxial Stress Strain Response of Granite Rocks." My name is J. Naveen Kumar. I am a research scholar at IIT Bombay. So these are the contents I am going to deliver: introduction, research gap, constitutive model used in the study, results and discussion, conclusions and future study and references. As we know that rock is a natural occurring material in the earth crust consisting of mineral grains which is bonded by strong internal cohesive forces generally found in large masses or fracture form. Based on the mode of formation, we have igneous, sedimentary and metamorphic rock. And as a geotechnical engineer, the study of rock means to understand the mechanical behavior under various stress conditions and to analyze the mechanical properties of the rock and its suitability for engineering purposes in terms of strength, deformation, permeability and durability. Naturally, the rock gets stressed in different stress conditions, either uniaxial, biaxial, triaxial and polyaxial. The example for uniaxial stress condition is nothing but the rock at the deep mines will get stressed due to the high overburden pressure, and the simplest representation is the laboratory test. And whereas in the case of biaxial stress condition, we can see at the surface of the tunnels. Triaxial stress condition can be seen it is a general at a large depth where the rock gets confined from the three directions, either isotropically or anisotropically. Polyaxial stress condition can be seen at the fault locations where due to the seismic action during the earthquakes, at the fault location, the rock get stressed in more than three directions. Constitutive modeling is a concept or a way for developing the mathematical relation or the equations to describe the mechanical behavior of the rock under various stress conditions. We include either stress strain parameter or stress deformation parameter. We have a bottom line that a constitutive model for rock provide framework for predicting how type of rock responds to applied stress. Ultimately, it will be contributing to the safety and effectiveness of the engineering projects. Whatever the equations we are developing, ultimately it needs to be used in the design, and indirectly it will be contributing to the safety and effectiveness of the engineering projects. So researchers have come up with various constitutive models to predict the behavior of the rock under compressive stress, but many of these models were confined to a particular rock type or a particular stress condition or particular location. So in tradition way, we are initially analyzing the mechanical properties from the by test, and then we are developing the constitutive models. There is a scope if two materials are having the similar mechanical behavior, then the constitutive model which is developed from the for material 1 can be used for material 2 with the required modifications. Considering this as an objective, this study adopts an elastic constitutive model developed for concrete, plain cement concrete, to predict the behavior of intact granite rock. So here are the plots taken from the two references. Here we can see, irrespective of the Young's modulus, the axial stress strain behavior for the two materials, irrespective of the Young's modulus. So it is showing a approximately linear behavior till the peak stress or maximum stress. So considering this, Gokulnath et al. 2019, they developed a model for plain cement concrete by considering the properties from uniaxial compressive testing and equibiaxial testing, and they have come up with a constitutive model, and they have validated for three stress combinations. One is compression, 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 tension, and tension, tension. And it is suggested that for all these three stress combinations, the theoretical curve obtained from the constitutive model is giving a close alignment with the test response. To use this model for the rock material need to follow some assumptions. One is it should be homogeneous, either crack-free or intact. Second, it should be isotropic. The properties should be same in all the directions. And the non-dissipative nature, that we are assuming that whatever the if the rock gets stressed, the proportional amount of strain need to be produced from the rock. And the last one is valid up to the peak stress. So we are whatever after the peak or maximum stress, it is out of scope for this model. So here we can see the model. We have a stress tensor as a function of strain tensor linked with the two variables, that is K and M. So here K is trace of sigma. So since I am going to show the results of uniaxial stress condition, the stress tensor for uniaxial stress condition in the matrix form, it will be sigma 1 0 0 0 0 0 0 0 0. So if you take the trace of that, then we'll get the K1, similarly K2, K4. When we substitute the K values, then the model will be reduced in one variable, that is M. Here M is nothing but a material parameter. We have 5 material parameters, M1, M2, M3, M4 and M5. So these 5 material parameters are the function of the mechanical properties which are obtained from the material testing. So the 5 mechanical properties are initial tangent Poisson's ratio, initial tangent Young's modulus, maximum uniaxial compressive strength, lateral and axial strain corresponding to the uniaxial compressive strength. And the background of this model is in such a way that this model is not fully dependent on the stress tensor. It is also depends on the current density of the material. Here, indirectly it shows we have a 3 potential functions, that is phi g, and we have beta and also phi 1. So these 3 are the main material potential functions which will take the material response into the model, and then it will give the theoretical response. So here we have the equations for the phi g, phi 1 and beta are well established by the Gokulnath et al. For plain cement concrete. We are directly taking these equations to predict the behavior of the rock. But here there is a minor modification, is that here we have a power value of 5 by 2. This one is nothing but 2.5. So this 2.5 for a plain cement concrete, it can be applicable for all the stress conditions. But rock depends, the behavior of the mechanical behavior of the rock, it will depends upon the stress condition and geological location. It will varies from place to place. So the single value of 5 by 2 cannot be used universally for the rock. So we have replaced it with N, and then we have derived, and finally we got a generalized equation which can be used for both plain cement concrete and also for rock for all the stress conditions. Since I am going with a uniaxial stress condition, here I am taking M phi is equals to 0. And for the validation, we have considered 5 experimental responses from the literature, and we observed that whatever the theoretical response we obtained, it is also showing a close behavior with the material response that indicates that whatever the model we have adopted, it is giving a good result for the rock as well. And as I said, n value will vary. It is not a particular value. So here the n value ranges from 1.5 to 2, which is giving a good result. And corresponding this R square value in the case of axial direction, we can see around average of 0.98, whereas in the case of radial direction, we are getting around 0.9. So from this presentation, I conclude that whatever the model that we have adopted, it is giving good results for n value is equals to 1.5 to 2. And also we have further validated this model for sandstone in sedimentary category and marble in the metamorphic category, which is giving a similar type of results. And also we have extended this study in the triaxial condition to see the effect of confinement. And in that case also we have got the very appreciable results. And these are the references. Thank you.
Okay, thank you for the nice presentation. So any questions? Yeah, please go ahead.
Well, thank you for the nice presentation. I would like to ask, why are you interested only in pre-peak behavior and not the softening post-peak behavior?
Yes. So if we see the model, this model, like up to certain stage, we will get a positive response, but after that, it will take a negative response.
Yes, of course.
So when we are with this, we will get the response, but it will not give a good alignment with the experimental, whatever the experimental curve we will get. So
Yes.
that's why up to peak we are getting a alignment, but after the peak, it's different.
And you probably know why is that. It's because of the localization of deformation. There is a failure. So the one-to-one correspondence with a material model written at the point level mathematical equation fails to comply with the net response of the laboratory sample size specimen. Okay, that's the reason.
Thank you for your suggestions. Right.
Yeah. Any more questions? No? Okay, thank you.
Thank you.
So we'll go to the next presentation. So the next presentation is on rockfall hazard assessment and mitigation measures of Rasuvagadi hydroelectric project, Nepal.
Okay, thank you. Okay, very good evening to everybody. Thank you for Geotech Asia 2025. It's giving me opportunity to present here. And today I'm going to present rockfall hazard assessment and mitigation measures for Rasuvagadi hydroelectric project of Nepal. And introducing myself, Darshan Babu Adhikari from Chilme Engineering Services Company Limited. And also for the study, Dr. Mohan Prasad Acharya also, and from any engineering company limited. And first, I like to introduce you that Nepal. Nepal is a mountainous country. You can say that it is characterized by climatic conditions there is high steep relief conditions, slope, and high seismicity, and there are weathered and vulnerable rocks, which will making the more prone to rockfall hazards to all the infrastructure development projects. And annually, there are many rockfall events also occur in Nepal, especially in the highways and settlements and hydropower projects. That means especially on the developing infrastructure projects. And it's very challenging works to deal with the rockfall events for the infrastructure projects. And now I'd like to introduce the project. The project lies in the central Nepal. Central Nepal, that is in the Raswa districts and near the Nepal-China border. And Nepal has suffered, the 2015 Gorkha earthquake. That is a huge mega earthquake that is 7.8 magnitude. During that mega earthquake, there were the rockfall events caused in this project where there was under construction of the permanent camp facilities for the project team members. And due to the rockfall events that has caused not only the physical damage of the infrastructure, you can see here that has always damaged, and these all under construction projects buildings were stopped due to that raised safety concerns, and the construction activities were stopped. And for this response, the project has continuously monitored the slope conditions, including they have carried out drone-based surveys and carry out the identification of the potential source zone where that might cause fall the rocks from where, and the distance maybe, and where the rocks have already run out distance, and where the rocks have been placed after the events, where they are. And after that, then we study with the project. We study that there are 2 camps. Just earlier, what I discussed was of this Camp 1 facilities where the rockfall events have been occurred. And further, we studied then this one and another one, Camp 2, where some other facilities are also to be constructed. Okay. About the geology, this is lies in the Botekoshi River that is coming from China. That is the Kerung and Lende Pla that comes, and that is the Botekoshi River. There is a project, and it is characterized by the high, steep, mountainous terrain and steep slopes. There are the very fractured rocks, and this is the higher Himalaya sequence where the gray banded gneiss are intercalated, dark gray magnetite rocks are existed. They exhibit high. There are high levels of foliations with joints dipping the 45 degree to 70 degree. That means which is contributing to rock falls. Okay, and for the rockfall study, we do the field observations and data collections, topographic maps, drone-based topographic survey, and all the boulder survey as well, the size of the boulders that come to the infrastructures where it will hit, and all these observations and field investigations cause that we find out the source of the rock falls. Also for the Camp 1, we find the source, potential source in the elevation of 2400 to 25. There are the source, and for Camp 2, we have the source were found in these elevations. And the boulder measurements which were found in the impact zones, okay, that is above 1 meter size round. And this is the drone-based survey. This is the locations, and the permanent camp facilities were under construction were in these locations, and the rockfall events due to the earthquake that were coming from these locations and just impact here. So we have to study these areas. For this is the Camp 1, okay. And we did we did rockfall simulations using the GeoRock 2D and 3D software packages, and where GeoRock 3D allows the 3-dimensional analysis of rockfall tragedy that will provide the informations of the falling rockfalls, where it comes, and just what is the path of the rockfall tragedy, and selecting the critical locations of all the trajectories from 3D simulations. We use the 2D simulations which help to refine us in providing the mitigation measures. And for the simulation parameters, especially we use the block sizes which we found in the there, and the initial velocities and material properties of all the study area. In the modeling, we use a 1 meter size boulder with initial velocities of 1 meter per second in both the plane, and the coefficient of restitution where also we put the parameter that were set to replicate realistic rockfall behavior along the steep slope. That means we just back analysis and put the correct of all the practical that means boulder where the boulders reach during the event. And simulations were carried out, and then the back analysis and do the correct coefficient of restitution values were set. And this is the model. You can see this is for the Camp 1 model, and this is the Camp 2. You can see this is the set there. That means the Camp 1 areas, and this is the source zone and transferring zone for Camp 2 similarly. You can see for CAM2 there is some nose here, and that is diverting to two sides. But and after the nose, that will be coming to our impact zone. Sorry. Okay. And these are the simulations carried out in the 3D models. And for the 2D models, then after we select the critical profiles from the 3D models, then we do it. This one is for the CAMP1. In CAMP1, we just did the rockfall simulations, and we found that 75% of the falling rocks has reached this. This is the CAMP1 area, has reached there. Sorry, approximately 75% reached the camp area. So that means we have to do some mitigation measure here, so that 100% will not reach to the CAMP1. Similarly for the CAMP2 areas. And in this, for CAMP1 areas, the combinations of the all mitigation measures were introduced, and the simulations was further carried out. And we just introduced the Gaussian layers at the top near the source zone, where there is some flattened or benched zones there, and we just use the Gaussian layers, anchored Gaussian layers here, and then certain portions with the slope, all little mild slopes areas, we just change the fine debris or debris material, so that the energy will be dissipated. You can see here the simulations, all the rolling blocks are just hitting in this zone. That means that this is the critical zones, which from where that if it is, we have to reduce the coefficient of restitution here. So we just introduce the fine debris here, so that it will be that energy will be dissipated and will not reach to the CAMP1. And even some boulders or rock will be coming here, so the rockfall barriers of 3,000 kilojoules were introduced, and then did this, all the 100% of rockfalls impacting together were prevented and not coming to the camp areas. Similarly, for the CAMP2 portions, we did the slope here modifications. We did just in this hillside slope, we made the slope like a concave shape, so that all the coming from boulders will just impact here, and the energy will be reduced, and we fill the slope, modified slope with sand, so that the boulders energy will be dissipated. And further doing this also, there is 75% where work and 25% reach to the camp areas, and we further introduced the Gaussian wall there, and after that 100% were prevented. And now from all the study, the conclusions, we effectively find the rockfalls source zones, and effectively modeled the rockfall behavior and guided the mitigation design. And just not only the barriers or something, we have used the combined methods of the mitigation measures, so that it is effective. These are the Gaussians and concave plates and flexible barriers were introduced in there, that of the ETAC 2027 standards. And we just recommend that like this regular inspection maintenance are necessary, particularly post monsoons always. The study also underscores that the need of there is always need of the site specific design, so that in the like in our seismic activity zone, so that we can use the combined method of all the mitigation measures that can be used. And this also offer the practical guidelines for similar hydropower projects in similar geography regions in the mountainous terrains, and can just protect from the such kind of rockfall events. Overall, just enhances resilience and operational safety of the critical infrastructures. Now I'd like to acknowledge all these. This was the part of the study from the NE Engineering Company of our Raswagadi hydroelectric project, and both companies were highly appreciated for their contributions. And Dr. Mohan Prasad Acharya from NE Engineering, Nepal Geotechnical Society, and Chilime Engineering Services Company Limited, Chilime Jalavidyut Company Limited of Nepal. And these are the references. And thank you. Any questions?
Yes. You can please go ahead and ask your questions if you have any. Yeah. So I think this is actually one of the questions.
Thank you for the nice presentation. I have two questions.
Okay.
In your simulation, you consider the initial velocity. How do you determine the initial velocity?
This was considered different literatures, and then just assume that 1 meter per second in both directions. first starting.
Okay, so do you have any earthquake record? So you can use the earthquake record to determine the initial velocity.
Not.
No. Okay, and the second question is about the terrain. Do you use the digital elevation model or
Yeah,
digital service?
we are doing now right now. Still there is we are doing, and during this process, digital elevation model, and so that 3D model was developed from the DEM.
Okay, okay, thank you.
I have a
You had one question?
Sorry, I just missed the beginning of your presentation, but I'm curious to know if have you looked at adding reinforcement right at the source to reduce the rockfall hazard altogether?
Yeah, again.
So I may have missed the beginning of your presentation, but I'm just curious to know if you also considered adding mitigation measures right at the rockfall source zones in order to reduce the rockfall hazard.
Okay. Good questions. The source zone is very highly fractured zones and are maybe vertical, so that the constructioning doing the mitigation measure in the source zone, like in the like mating in the zone. That is quite not difficult for the construction activities, and this is for the projects, and that will also have the cost problem, and we have to do it optimized solutions. We have to do so. This is one.
Thank you.
Yeah, I have one question. So in one of the preventive measures, you mentioned that you have used gabion wall. What is the height of the gabion wall you have proposed?
Yeah, that is 6 meter height.
6 meters.
Yeah,
And the
for
thickness?
Camp 2.
Yeah, and the thickness?
Yeah, thickness also 6 meter, like like this one, this way. I go. I have not image here, but
Okay, fine.
the base is the 6 meter and height is also 6 meter. Just a triangular shape, gabion stepwise.
Okay, okay. Thank you.
Okay, welcome.
So this is the last one, right? Last. So yeah.
Thank you.
Yeah, you can go and have your seat. I'll call the next presenter. So the next presentation, this is the last presentation, I guess. The next presentation is on a mesoscale model for conglomerate and breccia rock fracture.
Yes.